So we have completed the check for prime. So apparently we have completed everything and the GCD or the HCF is left. So let's go across and learn the GCD or HCF and then come back and take it over. So what do you mean by GCD or HCF? It's very simple. Greatest common divisor or highest common factor. Let me give you an example. If I give you two numbers, n1 equal to 9 and n2 equal to 12. So you need to find the highest common factor or greatest common divisor that actually divides n and that divides 9 and 12. So if I write down all the factors of 9, it is 1, 3, and 9. If I write down all the factors of 12, it is 1, 2, 6, and 12. Even 3, 4. And these are all the factors of 12. So if I ask you the common factors, if I go ahead and mark, it is 1, 1, it is 3, 3. So there are two common factors. Out of these two common factors, which is the highest one? 3. So I can say the GCD of 9, 12 is 3 because 3 is the largest number that divides 9 and 12 both. If I ask you the GCD of 11 and 13, what will it be? It will be 1. Because if you try to write down all the factors of 11, it's going to be 1 and 11. All the factors of 13, 1 and 13. So the common one is just 1 and that is the GCD. So there will always be a GCD because 1 is a number that divides every other number. So for every given two numbers, there will always be a GCD or HCF. If I ask you what is the GCD of 20, 30 or rather 20, 40. What is the GCD of 20, 40? Because for 20, 20 is a factor and for 40, 20 is also a factor. So that's why 20. So for two given numbers, one of them can also be a GCD of those two given numbers. So that is what is the definition of GCD. So all of you know, so you know how to find factors of two given numbers. You're given n1 and you're given n2. So in the last two problems, you have learned how to find factors. So imagine it's like n1 is 9 and n2 is 12. So can I say, if I loop from 1 to 12, and for every number, I'll check if they're replaced by I to 3, n2 was given as 9 and 40. If I run till 20, that will work because 20 is the largest factor I can have. Running it for 21, 20 outside this break, this one, it will break out from this. How does it work? The minimum of 20, 40 is 20, n2 is 40, and I do the other way. Yes, I do the other way, and I say, I'll run it from n2 modulo I equal to 1, 4, trying to find highest. And over here, what are you doing? You're going from 1, 2, 3, 4, and you're checking everyone. But what if n1 is 20, n2 is 40, and I do the other way? Yes, I do the other way, and I say, I'll run it from minimum of n1, n2, I greater than equal to 1, I minus, and I'll say if n1 modulo I equal to 0, and n2 modulo I equal to 0, I will print that as my GCD, and I'll break. And you know what is the task of break? It always breaks out from the outer loop. Not, this is a conditional statement. This is not a loop. For this break, which is the loop that is outside this break, this one, it will break out from this. How does it work? The minimum of 20, 40 is 20. So 20. 20 modulo 20 equal to 0. Yes. 40 modulo 20 equal to 0. Yes. Print GCD as 20. Yes. Break. So the program terminates. In this way, you will say, in this way, it will have a better complexity because the moment you are getting someone from behind, it breaks out. You might give me this. Yeah, definitely this might turn out to be a better one for a lot of cases. But still, the worst case will be minimum of n1, n2. Imagine I give you two numbers. n1 equal to 11, n2 equal to 13. In this case, what will happen? For 11 and 13, the highest common factor is 1. It will start from 11, 10, 9, but will not find anyone till 1. So it will eventually loop from 11 to 1. So no matter what you do, the time complexity will be still this. Because if both the numbers have GCD as 1, it ends up running completely. The loop ends up running completely. And you know when you determine the time complexity, taught you in the time complexity lecture, you always take worst case. You always take worst case. The worst case is when you run it till 1. So we saw the previous method was a brute force method and was taking linear time complexity. It will start from 11, 10, 9, but will not find anyone till 1. So it will eventually loop from 11 to 1. If you want a mathematical proof of it, you can definitely Google search. There's a huge mathematical proof to it. Again, we will not go deep. If you're given two numbers n1, n2, the GCD of n1, n2, whatever is the GCD of n1, n2, that's equivalent to the GCD of n1 minus n2, n2. where n1 is greater than n2. Usually in books, you'll find them written as GCD of A comma B is equal to GCD of A minus B comma B, where A is greater than B. This is what the equaloidian algorithm states. If you want a mathematical proof of it, you can definitely Google search. There's a huge mathematical proof to it. Again, we will not go deep into the mathematical proof because it is not required in programming world. You just need this concept. So just have the concept. Now, if I try to prove this with induction, it's very simple. If I give you two numbers, imagine 15 and 20. It basically states the greater number and the smaller number. What is the GCD of 20, 15? We know the GCD of 20, 15 is 5. So it states the GCD of 20, 15, the greater number 20 and the smaller number 15 is equal to, it states greater minus smaller, 20 minus 15, 5, comma the smaller number 15. So what is the GCD of 5, that is also 5. So again, by induction also you can prove it. You can take any two numbers and you'll be able to prove that they are same. So I can say that the GCD of 20, 15 is equivalent to the GCD of 5, 15. Now, you apply the equaloidian on the first two numbers, and whatever you get, that will always be a truncated number. You saw 20 getting truncated to 5. Again, you will apply equaloidian to this. If you try to apply equaloidian to 5, 15, it has to be the greater number at first. So apparently you have to apply equaloidian to 15, 5 because 15 is the greater number, right? So what you do is you say, okay, let's apply equaloidian to 15, 5. They'll be like GCD of 15 minus 5, 10, 5. Again, you can apply equaloidian to 10, So if you apply equaloidian to 10, 5, it will be greater is 10, 10 minus 5 is 5, 5, 5. Again, if you apply equaloidian to 5, 5, it will be, both of them are same, anyone can be at the front, 0, 5. So 1 apparently is A equal to of, if it is 2, 10, and you go on doing till it becomes 0. After if I'm not given else, because if this line doesn't, if this line is given it in such a way, say, I just given B, can I say you go on till both of them are greater than 0? Very simple. And I know one of them will be greater. Either A will be greater. In that case, I'll do A modulo B. Or else if B is greater, I'll do B modulo A. Instead of swapping, changing, because I did not want to get into swapping, changing. Why? Over here it was 2, 10. So A was this, B was this. Then you swapped it to this. I did not want to implement that. I knew now 10 will be modulated. So what I did was I implemented it in such a way, stating is equal to A modulo B, B. That's a bit of and the logic is very simple.
the GCD. In this presentation, we have algorithm which is also called as Euclidean algorithm. Why we are focusing on this algorithm? This algorithm is for computing the greatest common divisor, simply GCD. This greatest common divisor is also known as the highest common factor, HCF. So whatsoever, the concept is the same. Whether you refer it with the name GCD or HCF, we are going to find the biggest number, the biggest divisor, that too the common divisor. If things are not clear, no worries. Let's understand the operation of GCD first. So we are in example 1 for understanding the GCD, the greatest common divisor. As I already mentioned, we are going to find the GCD of two different numbers, right? So and that's why I've taken two different columns. Firstly, I'm going to take two different numbers, right? Let's say the first number is 12 and the second number is 33. Now I'm going to find the GCD of 12 and 33. How to find this? I'm going to find the divisors first, then I'm going to find the common divisors, and then I'm going to find out the greatest common divisor. So this is so simple, Let's first 4, 6, we are done with example number 1, 5, and 25, right? And what about the number 3? In this example, we are going to take the question, find the GCD of 12, 33. If you note here, these two are not prime numbers, right? If these two numbers are prime numbers and these two are different numbers, then we can easily say the GCD is 1. But in this case, these two numbers are not prime numbers. So in this case, we are going to use Euclidean's algorithm or Euclid's algorithm for finding the greatest common divisor. So we are in method 1. So what we are going to do is just create 4 columns like this. The first one is the quotient. The second one is two parameters A and B, because we are going to compute the GCD of two different numbers, right? So 12 and 33, we have two numbers here. So we are going to take A and B as two variables here. And obviously we are going to do the division. Division has two outputs, right? One is the quotient and the other one is the remainder. So the first one is the quotient and the second one, this R, is the remainder. So just take 4 parameters like this in 4 columns: quotient, A, B, and remainder. Now we are going to take these two numbers, 12 and 33. Which is the biggest number in these two numbers? This is 33, right? Always use the biggest number in A and the next number in B. In this example, we have 33 as the biggest number. So A is 33 and B is 12. So let's do that now. So I am taking the biggest number 33 in A and the smallest number 12 in B. Now do the division operation, and whenever you find this B becomes 0, then whatever is there in A, that is the GCD. I repeat, do the division operation. Whenever you find the B parameter with 0 as the value, A mod B, right? You are going to do the operation A mod B. This is A divided by B, right? So 33 mod 12. So when you divide 30, so we are going to, first row is over. Are we getting B as 0 here? No, we have to repeat the operation. Just see here, let this B go to this place, that is B is A now and the remainder is B now. I repeat, B is A now and the remainder is B now. Just shift the values. So when you shift the values, 12 will be in A and the remainder is 3. So this 1 is the quotient and 3 is the remainder. So we know what we will get here and here, right? So 1 is the quotient and 3 is the remainder. Are we getting B as 0 here? No. So we are going to repeat the operation. So 9 is going to be placed here and 3 is going to be placed here. See what is happening? 9 is going to be placed here and 3 is going to be placed here. So 9 and 3 are taking the places of A and B respectively. Now, so we are going to T as the remainder. So 1 is the quotient and
Hey everybody, this is Paul. In this tutorial, I'll be showing you how to find the greatest common denominator by using the Euclidean algorithm. So 10 times, how many times 10 goes into 45 times some number q, so in this case it's going to be 45, and then we set it equal to the smaller number times some number q plus some number r. So the q is how many times 10 goes into 45. The r is the remainder of that result. So for our case, it's going to be 45 is equal to 10 times 4 plus 5. 10 goes into 45 4 times with a remainder of 5. So the next step and all the remaining steps is we take the number that's in this position and we move it to where this number was on the left-hand side. And then we take our remainder and we move it to where this number was. And we just kind of follow this pattern all the way down until we get a remainder of 0. So for our case, we're just going to get rid of the 45 and move the 10 where the 45 was. And then the 5 goes where the 10 was. So now we're asking ourselves, 5 goes into 10 how many times? 2 times with a remainder of 0. So now that we have a remainder of 0, we simply look back at the previous remainder, and this is our greatest common denominator for the original two.
So Armstrong number is completed, and the next problem that we GCD, the other is GCD. Simple. As simple as this. If I try to, so Armstrong number is completed, and the next problem that we will be doing is print all divisors. So when I say print all divisors, what does it mean? Imagine I take a number like 36 and ask you, what are all the numbers that divide 36? So you can say 1 is something which completely divides 36. You can say 2 is something which completely divides 36. You can again say 3 is something which completely divides 36. 4 is something which completely divides. Is 5 something which completely divides 36? No. If 36 is divided 5, it leaves a remainder of 1, so not 5. 6 is something which does it. 9 is something which again does it. And 12 is something which does it. Then 18 is something which does it. And then 36 is something which does it. So if I talk about 36, the divisors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. These are the divisors of 36. The question is very straightforward. You have to print all of them in this particular order. Okay. Now, how do I do it? It's very simple. One thing I know for sure is if I'm talking about divisors or factors, they're definitely going to lie between 1 to the number itself. Can I say all the divisors will be between 1 to n itself, because anything greater than n will never divide n for sure. So if I know all the divisors are going to be between 1 and n, can I just loop from 1 to n? That's my first thought process. Since I know the divisors are from 1 to n, my first thought process is very simple. So let's do one. Let's start the loop from I equal to 1, I lesser than equal to n, and I plus plus. This is something I know for sure. So I is used to loop around. Now the first value of I is 1, then it's 2, then it's 3, then it's 4, then it's 5, and then so on till 36 in this case, if it is n. So how do you determine that this I is a part of all the divisors? It's very simple. Can I say if it is completely dividing, if I is completely dividing n, then it is a factor or a divisor. And what do you mean by completely dividing? It should leave a remainder of 0. When I say leaving a remainder of 0, does it mean if I do a modulated of I, if I do n modulo I, the value should be 0 because it's completely divisible. By what I will do is I'll say, okay, if n modulo I is equal to 0, I will go ahead and print I in C++ out in Java system.out.println. I'll go ahead and print out I. So in this way, I'll be able to print all the factors of a particular n. Now, if I talk about the time complexity, ask you what is the time complexity of this code? You'll be like, Stripe, it's very simple. Since the loop is running from 1 to n, it's taking n iterations. And this is an unit operation, so let's not calculate it. Thereby, the time complexity of this particular approach is nothing but big O of n. Very simple. Over here, they've given us everything. They want us to write this print divisors function. Let's write the print divisors function. It takes an n. And as I said, it's very simple. You go from 1, you go on till n. And you say, this one requires a bit of mathematical observation. Let's see that mathematical observation. So for 36, I said that 1 was a factor. If 1 is a factor, 1 has to be multiplied with something in order to get 36. So 1 was multiplied with 36. And if you carefully observe, if this is 1 and the number is 36, the other number will always be n by 1. Very simple. If it is 2, the other number will be n by 2, which is 36 by 2. That means 18. So you get 18. The next time it was 3. So the next time it is 3. So when I take 3, it is nothing but 12, 36 by 3. Because 3 into 12 will be 36. The next time when I take 4, it is 4 into 9. The next time when I take 6, it is 6 into 6. Next time, the next factor is actually 9. And then you multiply it with 4. And the next factor is 12 and you multiply it with 3. And the next factor is 18, you multiply it with 2. And the next time it is 36, you multiply it with 1. So if I have to write all the factors, these are all the factors. These are definitely all the factors, right? But do you have a bit of observation? If I draw a line at this portion, and I take this, aren't they equal? 1 into 36, 36 into 1. So can I say, even if I consider everything before the orange line, I will get 1, I'll get 2, I'll get 3, I'll get 4, I'll get 6, I'll get 9, I'll get 12, I'll get 18, and I'll get 36. Even if I take everything before the orange line, even if I take everything before this orange line, do I get all the factors? I do. So do I need to go beyond this orange line? No. So what is this orange line? If you carefully observe, what are you doing? A small number into a big number, a small number into a big number, a small number into a big number, same number. And then a big into small, a big into small. Beyond square root, the numbers will grow. Square root of 36 is 6. Beyond square root, the numbers will grow. And it will nothing but a replication of the upper half. So thereby, this is nothing but a repetition of the upper half. Thereby, I can say, even if you loop till square root of n, you actually can get your factors. How? If this is 1, this has to be n by 1. If this is 2, this has to be n by 2. If this is 3, this has to be n by 3. If this is 4, this has to be n by 4. If this is 6, this has to be n by 6. So can I say, now the looping is going to be very straightforward. I loop from I equal to 1 till I less than equal to square root of n and I plus plus. Can I do? And can I say, if n modulo I is a factor, then print I as one of the factors. What is the other factor? We just now found out the other factor was n by I. But we need to be careful. What is the careful observation? If it is 6, the other factor might be 6. So they are not two different factors. So if you're taking the second factor to n by I, just make sure that n by I is not equal to I, because the second factor might turn out to be the same factor. It's very important. The n by I, which is the second factor, must be compared with I. And if they're not same, you can say that maybe print. That's your another factor. That's it. So first, check if I is a factor, print it. Now the other factor, n by I, with if you're taking the second, we need to be careful. What is the careful observation? If it is 6, the other factor might be 6. So they're not two different factors. So if you're taking the second factor to n by I, just make sure that n by I is not equal to I, because the second factor might turn out to be the same factor. So it's very important. The n by I, which is the second factor, must be compared with I. And if they're not same, you can say that maybe print. That's your another factor. That's it. So first, check if I is a factor, print it. Now the other factor, n by I, with which the I will be multiplied, just check if this is not equal to I. If it is not, that's the second factor. That's it. So if you go ahead and print this, the printing will be something like this. First 1 and 36 will get printed. Next 2 and 18 will get printed. Next 3 and 12 will get printed. Next 4 and 9 will get printed. Next one I is 6. 6 gets printed, but the other factor is 6. And it fails this condition check. Thereby, the other 6 doesn't get printed. So all the factors are printed, but they are not printed in a proper, they're not printed in a sorted way. So what you can do is, whenever you are getting all the factors, probably you can store the them into a data structure. And if you have seen the C++ STL video, you know which data structure you can use. You do not know what will be the size or what will be the number of factors. So the data structure that you will be using is a list in Java or a vector in C++. You'll be using an undefined, like you cannot define the size of the data structure. You'll be using a list, okay? And in that list, you can store it, store. So everything will be stored in the list. Once you have stored in the list, sort the list. And if you sort the list, you will get everything in the sorted fashion. So if I go back to the code, what did I say? We will be going till square root of n, right? We'll be going till square root of n. We know this is a factor and we need a list now. So let's take a list. So this is our list vector. Go ahead and say over here, sort ls